Hello there, I'm Dylan, and welcome to this fifth lesson in the Introduction to Functions. This lesson is called Using Functions, and we're going to see how we can practically apply functions and their graphs to our daily lives. By the end of this lesson, you should be able to understand and interpret graphs and analyze the information shown on a graph. Let's revise function notation by having a look at your task from lesson 4. You were given this information and you were asked to find the dosage if the mass were 6,9 kilograms. So the dosage depends on the body mass, but the body mass is independent of the dosage. So we're going to choose X for our body mass. I'm going to write here that body mass is given by X kilograms. And just note that I'm writing kilograms over here so that I do not need to rewrite it again in the formula. Now the dosage or the output value is dependent on the body mass. Now to write this relationship or function, I need to give it a name. I'm going to call it Q for quantity. Now Q of X represents the result when the function works on X. So it represents the number of milligrams of medication for a mass of X. In other words, Q of X is the number of milligrams of medication. So using the information we have been given, we can say that Q of X is equal to 2,1 plus 4,6 multiplied by the body mass, which we know is X. Remember that function notation helps us to write things simply and clearly. So in our case, we're dealing with the function Q of X, which remember is equal to 2,1 plus 4,6 X. And we're dealing with a body mass of 6,9 kilograms. So we know that X is equal to 6,9 kilograms. Now what we need to do is substitute this into our formula. So Q of 6,9 is going to be equal to 2,1 plus 4,6 multiplied by 6,9. Now in solving this, we need to remember to estimate. I know that 4 times 7 is 28 and 5 times 7 is 35. So my result is going to lie somewhere between 28 and 35. Now normally you would do this with a calculator, and Q of 6,9 would be equal to 2,1 plus, and if you calculated this on a calculator you would find that the answer is 31,74. Therefore finally Q of 6,9 is equal to 2,1 plus 31,74, which is a grand total of 33,84. For the second part of the task, we have an output value and we need to calculate the input value. The prescription states a dosage of 48,1 milligrams, and we need to make sure that the patient has the correct body mass for this dosage. This is the formula we're working with originally, but now we also know that Q of X is equal to 48,1 milligrams. We have been given our output value. But now in both of these formulae, Q of X is the same. So we can therefore say that 2,1 plus 4,6 multiplied by X is equal to 48,1. So I simply now need to solve for X in this equation. I'm going to subtract 2,1 from both sides of the equation. I will get 4,6 multiplied by X is equal to 46. Now, what number multiplied by 4,6 is equal to 46? Well, that should be easy. Obviously, the answer is 10. So therefore, X, in other words, the body mass, is equal to 10 kilograms. So when the output is 48,1 milligrams, the input is 10 kilograms. So that's like saying that if a patient were to receive a dosage of 48,1 milligrams of vitamin AA, her body mass should be 10 kilograms. Now in lesson 3, we plotted the graphs of some of our functions, And we saw that in those cases, all of the graphs were straight lines, because for a 1 unit change in the input values, the output values changed by a constant amount. If you have a look at our formula here, our constant rate of change is 4,6. Therefore, this would also be represented as a straight line because it is a linear function. However, not all functions are linear, and therefore not all graphs are straight lines. You need to make sure that you can interpret the data on any graph. Now, mathematics is all around us all of the time, and to understand what is happening, you need to make sure that you can interpret data. And I'm sure all of you have heard about income tax. Now, income tax is payable according to rates set by the revenue services. Let's have a look at how this is reflected and represented in a graph. When you look for a job, it is a good idea to know how much tax you will pay for a specific salary that you earn. That way, you can plan ahead. Here we see that the higher your income is, the higher the amount of tax you pay. Although the graph is a straight line in places, the entire graph is not a straight line. As with tax calculations, there are many situations when the relationships between variables is not linear. For a nutritional supplement that we'll call vitamin AA, the body has different requirements at different ages. The pamphlet shows this graph. To interpret the graph, we need to look at a number of aspects. All of the graphs we looked at thus far have consisted of solid lines, continuous lines. This graph, however, is made up of a series of discrete points. Let's quickly define the word discrete. A discrete function has values that are separate and distinct. On the graph for the dosage of vitamin AA, the values along the x-axis represent whole years, but it's important to note that the points in between have no meaning at all. So let's look at some values. When the age is 7 years, we can see that the number of milligrams required is 800. The dosage in milligrams is thus dependent on the person's age. So we can see that for babies, they need a large number of milligrams of vitamin AA. And for the ages of 1 to 18, we can see that the function is decreasing. So as you grow older, you tend to need less and less of vitamin AA. From the age of 18, however, we can see that the function is constant. In other words, if you are 18 or 22 or even 72, you need the same number of milligrams of vitamin AA. You need to learn the following. For a decreasing function, as the input values increase, the output values decrease. A value that does not change is constant. The graph shows that for 1-year-old babies, the dosage is 1,300 milligrams. We say that 1,300 milligrams is the maximum output value. From the age of 18, however, the requirement is constantly 400 milligrams. In other words, the dosage is never less than 400 milligrams, and so we say that this represents the minimum output value. Remember that the maximum refers to the biggest output value and the minimum refers to the smallest output value. This function reaches a maximum output when the age or input value is 1 year, and the function reaches a minimum value when the age is 18 or more. Let's interpret the graph of another function. This time we're going to have a look at a graph showing the growth rate of bacteria. Unless treated, specific bacteria grow at the unusual rate shown in this graph. This function is also nonlinear. Because the bacteria grow continuously, in other words all the time, the function is continuous and the graph is a solid line. The number of bacteria is dependent on the time in which they have been allowed to grow. As time increases, the number of bacteria increases, so this is an increasing function. Let's analyze the growth of bacteria here on an accurate graph. After 3 seconds, what is the number of bacteria? Well, you need to look at the corresponding output value. So when t is equal to 3, the number of bacteria or output value is 15. Now, if the number of bacteria or output value is 35, we can see that the corresponding input value is 5. This means that after 5 seconds, the number of bacteria is 35. Now, clearly, the graph is not a straight line, and so the formula is not linear. Now, let's investigate this by looking at a table of values. As before, we will consider when the input values are changed by 1 unit to see what effect this has on the output values. So here is a table of my input and corresponding output values of the graph that I've just seen. Notice though that the number of bacteria is never 0, so this has been left out. Now, for the first unit change in the input values, we can see that the output changes by 3 to 8, it changes by 5 units. The next unit change in the input values results in a change from 8 to 15 in the output values, in other words, a change of 7. The next unit change in the input values results in a change from 15 to 24 in the output values, in other words, a change of 9. And the last unit change in the input values makes the outputs change from 24 to 35. In other words, there's a change there of 11 units. Did you notice a pattern? The changes were not constant, but they did form a sequence. Let's have a look at how the changes changed. So we're looking at the pattern in these numbers. Remember, these numbers represent the rate of change of this function. And we can see that the change between 5 and 7 is 2 units. Again, the change between 7 and 9 is 2 units. And lastly, the change between 9 and 11 is again 2 units. So what have we just seen? Well, we saw that the rate of change of this function was not constant. But when we had a look at the rate of change of the rate of change, we saw that it was constant. It was always 2. In this situation, the formula is said to be quadratic, and the graph representing the formula, we call that graph a parabola. For the growth of bacteria, we would not consider negative time values. But this is what the entire graph looks like if we zoom out. Remember this example of a parabola shown in the growth rate of bacteria, because it is a function which you will use often. Now, in closing, I want to encourage you to take another look at the graphs in your textbooks, in the newspaper, and even on TV. Try and learn to interpret what the graph is telling you about the input and output values and the relationships that exist between them.